Good morning, everyone. In the previous class, we started talking about natural response in case of parallel RLC. And we have already derived three different equations. I said if I have parallel RLC, like what we have here, and we don't have external voltage or current source connected, it means we are talking about natural response. So we try to derive the equation of the voltage V of t, and we said that V of t could be represented by one of three different equations based on alpha and omega. What is alpha? Alpha is equal to 1 over 2 RC, and omega is equal to square root of 1 over LC. We said that if alpha square is greater than omega, so we are talking about a case which is called overdamped, and the equation for the voltage is V of t is equal to A1 times e to the power st plus A2 times e to the power s2t. And for finding the value of A1 and A2, we use the initial conditions, V of 0, which is equal to A1 plus A2, and dV of 0 by dt, which is equal to S1 A1 plus S2 A2, which is equal to the initial current in the capacitor divided by the capacitance. By solving this equation and that equation, we can find A1 and A2, and at that time, V of t is equal to A1, which is found from these two equations, times e to the power S1t, whereas S1 is equal to negative alpha plus square root alpha square minus omega O square, plus A2 times e to the power S2t, whereas S2 is equal to negative alpha negative square root of alpha square minus omega O square. But if alpha square is greater than omega O square, then this case is called underdamped case. And at that time, V of t is described by this equation, which is beta 1 times e to the power negative alpha t multiplied by cosine omega dt plus beta 2 times e to the power negative alpha t times sine omega dt. Whereas omega d is equal to the square root of omega O square minus alpha square. Again, for finding beta 1 and beta 2, we are using the two initial conditions, V of 0, which is equal to beta 1, and dV of 0 by dt, which is equal to negative alpha beta 1 plus omega d beta 2. But if alpha square is equal to omega O square, this case is called the critically damped, and the solution for the voltage V of t is equal to constant d1 times t times e to the power negative alpha t plus d2 times e to the power negative alpha t. Whereas d1 and d2 are constants again, and we are finding them by using the initial conditions. V of 0 is equal to d2, and dv by dt of 0 is equal to d1 minus alpha times d2. This is in case of we are talking about natural response RLC parallel circuit. What about if we are talking about also RLC parallel, but in that case, we are not talking about natural response. We are talking about forced response. And as a special case, we are talking about step response, whereas IF is equal to constant. So imagine we have similar circuit that has what? That has RLC connected parallel, but I have external current source connected in parallel. Right now, we are talking about step response, and there is a condition to use the equations that I'm going to talk about them. This condition is I have current source connected in parallel. If I have voltage source, I have to convert it to current source to be able to use the equations that I'm going to talk about them. So what am I going to do? I'm going to repeat the same story that I did before in case of natural response, RLC. And then I'm going to derive three different equations based on alpha and omega. So the first step for solving such a problem is to calculate alpha and calculate omega. So what is alpha? Actually, alpha in case of parallel RLC is equal to 1 over 2RC. And what is omega? Actually, omega O is equal to square root of 1 over LC. If alpha squared is greater than omega O squared, which is the first case, which we described it before as it is called overdamped, then the current in the inductor IL of T is equal to the forced current IF plus constant multiplied by e to the power S1 plus another constant multiplied by e to the power S2T. Again, from where I could find A1 and A2 or A1 prime and A2 prime. A1 and A2 are new constants. That's why I'm calling them A1 prime and A2 prime, because they are different compared to the natural response. Again, for finding them, I have to use the initial conditions. I have to use IL of 0 and DIL of 0 by dt. From where I can find DIL, so DIL of 0 by dt is equal to V over L. What about IL of 0? Actually, IL of 0, I could find it from the data that I'll give you in the problem, or it could be given, or I have to calculate it. So the first step for solving such a problem is to calculate alpha and omega. And then I will compare between them. If alpha is greater than omega, at that time IL of t is equal to IF plus constant times e to the power S1 2 S1t plus another constant times e to the power S2t. But what about if I calculated alpha and omega and I found that alpha squared is less than omega O squared? At that time, we are talking about the second case, which is under damped condition. I have two complex conjugate solutions for S1 and S2. Based on that, my solution IL of t will be equal to IF plus constant beta 1 prime times e to the power negative alpha t times cosine omega dt. Again, cosine omega d is a square root of what? It is a square root of omega O squared minus alpha squared plus beta 2 prime times, which is another constant, times e to the power negative alpha t multiplied by sine omega dt. Again, how to find beta 1 and beta 2 prime? From the initial conditions. And the last case is if alpha squared is equal to omega O squared. At that time, the solution IL of t could be represented as IF plus d1 prime t times e to the power negative alpha t plus d2 prime multiplied by e to the power negative alpha t. Again, d1 or d2 prime, I'm finding them from the initial conditions. If you try to look to the problem, it is similar, or this case, it is similar to RLC parallel, but in case of natural response, the only difference is in case of natural response, we are finding the voltage. But in case of natural response and in case of step response, we are finding the current in the inductor. Because those equations are derived based on the current in the inductor. Now, let us repeat the same story, but we will talk about natural and step response in case of series RLC. So we have covered parallel RLC, natural and step response. In case of natural, we are talking about the voltage. In case of step response, we are talking about the current in the inductor. This is the formatting that I'm using, and I have to have parallel RLC. 1R, 1L, 1C. If not, I will try to simplify my problem to have that. Right now, I'm going to repeat the same story in case if I have series RLC. And based on that configuration, I'm talking about what? I'm talking about natural response. So in case of natural response, I'm going to repeat the same story that I did before. So what do you want? I would like to find the solution for this problem. The solution for this problem for finding what? This is series RLC, so I'm looking for finding the current here, the current in this circuit, I of t. What is given? What's given is the initial voltage across the capacitor, V0, and the initial current in the inductor, I0. So I'm going to say summation the voltage in this loop is equal to 0. The voltage across the resistance is equal to Ri. The voltage across the inductor is LdI by dt. And what about the voltage across the capacitor? Actually, the voltage across the capacitor is equal to 1 over C integral of I dt plus the initial condition. Again, if I would like to solve that problem, I'm going to say summation the voltage across this loop is equal to 0. The voltage across this guy is equal to IR. The voltage across this guy is LdI by dt. The voltage across this guy is equal to 1 over C integral of I dt plus the initial voltage. Okay, now I have this equation. What is needed? I would like to solve it. We studied before for solving differential equation like that. I have to find the derivative again to cancel this integral. So the derivative of this with respect to time will be r di by dt because r is constant. Then the derivative of this again will be L di square by dt square. And then the derivative of VO is 0, but the derivative of this will be I. So I will have I over C. I will simplify this circuit, or this equation, sorry, and rewrite it again. If you try to simplify this equation, it could be written as di square by dt square plus, so I will divide all terms by L. So this guy will be R over L, L over L, I over LC. And this is what I did here. Again, this is second order differential equation. How to solve it? Like what we did before, we are going to assume the solution, which is I of t is equal to constant times e to the power st. Then I will substitute in this equation by I. Then I will have second degree polynomial equation. Then I'm going to find S1 and S2. So for solving such a problem, I'll do what I did before. Here, when we were talking about the voltage, we assume the solution. This is what I'm going to do. And then we try to substitute and we found a specific equation. This is what I'm doing here. I'm going to assume my solution I of t is equal to what? It is equal to a times e to the power st. Then substitute by that here in this guy. Oh, so this is I. Sorry, this is I over LC. Then try to solve for finding S. If you try to solve for finding S, you will find that S1 and 2 is equal to negative R over 2L plus or minus square root R over 2L square minus 1 over LC. For simplicity, I'm going to assume that this guy is alpha and the square root of this guy is omega O. Then alpha here in case of series is not the same like alpha in case of parallel, because in case of parallel, we said that alpha is equal to 1 over 2 RC. But here, based on my equations, alpha is equal to R over 2L. And omega is the same in case of parallel. Similar to the parallel case, 1 over square root LC. Again, based on alpha and omega, I can say I have different solutions. If alpha square is greater than omega, I'm repeating what I did before. It is overdamped case. Then I of t is equal to a1 e to the power s1t plus a2 times e to the power s2t. Case 2, if alpha square is less than omega o square, it is underdamped case. And I of t is equal to beta 1 times e to the power negative alpha t times cosine omega dt plus beta 2 times e to the power negative alpha t sine omega dt, whereas omega t is equal to omega o square minus alpha square under the square root. But if alpha square is equal to omega o square, this is the critically damped case, and the solution I of t is equal to d1t times e to the power negative alpha t plus d2t times e to the power negative alpha t. Again, from where I can find a1 or a2 or beta 1 and beta 2 or d1 and d2 from the initial conditions, I of 0 and di of 0 by dt. This is in case of what? In case of we are talking about series RLC, natural response. Again, the difference between this circuit and the previous one, which is parallel, we were calculating the voltage in case of natural response for parallel RLC. But here we are calculating the current. The second difference is, the second thing is alpha here. It is equal to R over 2L. But in the previous case, alpha was equal to 1 over 2 RC. Then based on that, I can choose one of three solutions. So the first step for solving any problem like that is to do what? To calculate alpha and omega. Then compare between them. And based on that, I can choose one of these three different solutions. And after that, I have to calculate the constants. A1 and A2, or beta 1 and beta 2, or D1 and D2. We are calculating those constants based on what? Based on the initial conditions. I of 0 and the I of 0 by dt, which is equal to VL of 0 over L. Now, what about if I have series RLC step response? In case of series RLC step response, the formatting of the circuit is I have external voltage source. What about if I have current source or anything else? I have to have that formatting because we derived our equations based on that circuit. So if you try to do the same, what you are going to have is you are going to find you have three different cases. You will calculate alpha and omega. If alpha is greater than omega, then this case is overdamped case, and the voltage across the capacitor is equal to the forced voltage, which is the given voltage, Vf, plus constant times e to the power s1t plus another constant times e to the power s2t. If alpha square is less than omega o square, you are talking about underdamped case, and Vc of t is equal to Vf plus beta 1 times e to the power negative alpha t cosine omega dt plus beta 2 prime times e to the power negative alpha t sine omega dt. Again, A1, A2, beta 1, beta 2 primes are constants. From where we can calculate or find them, actually, we can find them from the initial conditions. If alpha is equal to omega, this case is called the critically damped, and based on that, I can say Vc of t is equal to Vf plus constant times t times e to the power negative alpha t plus another constant times e to the power negative alpha t. So let me conclude for you what I have to do for solving any problem. So before we have already derived the equations for RL or RC. But for RLC, we have two different versions because it could be parallel, could be series. So if we are talking about natural response, RLC, but this is parallel or series, parallel circuit. So my circuit looks like what? Looks like that. I would like to find the voltage V of t. This guy is R, this guy is L, this guy is C. Now, the first step for solving such a problem is to calculate alpha, which is equal to 1 over 2RC, and then omega O, which is equal to square root of 1 over LC. And if you would like to calculate S1 and 2, it is equal to negative alpha plus or minus square root of alpha square negative omega O square. And then you will say if alpha square is greater than omega O square, this is the next step, then your solution V of t will be equal to A1 times e to the power S1t plus A2 times e to the power S2t. And this case is called over-damped case. And how to find A1 and A2? We are finding them from the initial conditions. We will say V of 0 is equal to A1 plus A2. And also dV of 0 by dt should be equal to S1 A1 plus S2 A2. Then solve these two equations for finding A1 and A2. And this will be my solution, and this is the end of the story. This is V0 positive. Now, if alpha square is less than omega O square at the time, this case is called under-damped case. And based on that, I can say V of t should be equal to beta 1 times e to the power negative alpha t cosine omega dt plus beta 2 times e to the power negative alpha t times sine omega dt. What is omega d? Actually, omega d is equal to square root of omega O square minus alpha square. And how to find beta 1 and beta 2 from the initial conditions? I will say V of 0 positive is equal to beta 1, and I can say dV of 0 by dt should be equal to negative alpha beta 1 plus omega d beta 2. This is the second equation. The third scenario, or the third case, is if alpha square is equal to omega O square. In this case, is called critically damped. And based on that, I can say V of t should be equal to D1 times t times e to the power negative alpha t plus d2 times e to the power negative alpha t. And from where I can find d1 and d2 from the initial conditions again. This is d2, and dv of 0 by dt should be equal to d1 minus alpha d2. This is in case of what? In case of we are talking about parallel RLC step response, I can choose one of these three different cases based on what? Based on alpha and omega. I have three different cases based on alpha and omega. I can choose one of them. So the first step for solving the problem is what? Is to calculate alpha and omega. And based on them, I can choose which direction, case 1 or case 2 or case 3. What about if we are talking about step response parallel RLC? So for a step response parallel RLC, my circuit looks like what? My circuit looks like that. I have resistance, I have inductance, and I have capacitance, and this guy is IF, this is C. And I'm looking for calculating IL of T. Again, I have one of three conditions. After calculating alpha, the first step is to calculate alpha, which is equal to what? Which is equal to 1 over 2 RC. And omega, which is equal to what? Square root of 1 over LC. And then S1 and 2 are equal to negative alpha plus or minus square root of alpha square negative omega O square. And then I can choose one of three cases. If alpha square is greater than omega O square, this is the first case, IL of T should be equal to IF plus A1 prime times e to the power S1T plus A2 prime times e to the power S2T. From where I can find E1 and E2 prime? From the initial conditions, like what we did here. But here we used V, but in this case we are going to use I of 0. So I can say IL of 0 is equal to A1 prime plus A2 prime. And the first derivative, dIL of 0 by dt, is equal to A1 prime is 1 plus A2 prime is 2. So from the initial condition, I can find also dIL of 0 by dt, which is equal to VL of 0 divided by L, because V is equal to LdI by dt. Then I will find the first derivative for this equation, which is equal to A1 prime is 1 plus A2 prime is 2. Then solve them for finding A1 and A2. This is the first case. The second case is if, and this is the overdamped case. The second case is if alpha square is less than omega O square. At that time, I can say IL of T should be equal to what? IF plus beta 1 prime times e to the power negative alpha T multiplied by cosine omega dt plus beta 2 prime times e to the power negative alpha t times sine omega dt. What's omega d? Again, omega d is equal to square root of omega O square minus alpha square. Again, from where I can find beta 1 and beta 2 from the initial conditions, IL of 0 and the IL of 0 by dt. The third case is if alpha square is equal to omega O square, at that time I can say that IL of t, which is the critically damped case, is equal to IF plus D1 prime multiplied by t times e to the power negative alpha t plus D2 times e to the power prime negative alpha t. Again, from where I can find the value of D1 prime and D2 prime. Actually, if you would like to find the value of D1 prime and D2 prime, you can use the initial conditions. These are the three different cases. In case of we are talking about parallel RLC, but in case of what? In case of step response. Let us see similar case in case of natural response and step response, but we are talking about series RLC. Similar cases. So now we are going to talk about natural response of series RLC. As a conclusion, the circuit will look like that. So if I have a problem like this one, and this is R, this guy is L, this guy is C. If you would like to find the current I here of T, what you have to do, you will calculate alpha first, which is equal to R over 2L. It is different than the previous alpha. And omega O is equal to 1 over square root LC, or square root of 1 over LC. And then I can calculate S1 and S2, so I can say S1 or 2 is equal to negative alpha plus or minus square root of alpha square negative omega O square. Then I have three different cases. If alpha square is greater than omega O square, at that time, I can say I of t is equal to A1 times e to the power S1t plus A2 times e to the power S2t. And then how to find A1 and A2 from the initial conditions again. And if alpha square is less than omega O square, then my solution I of t will be equal to beta 1 times e to the power negative alpha t times cosine omega dt plus beta 2 times e to the power negative alpha t multiplied by cosine omega dt. E to the power negative alpha t multiplied by, let me go back to this guy, t multiplied by e to the power negative alpha. This is in case of alpha square is equal to omega O square. This is the case. Oh, what is that? Oh, I went back. Oh, he didn't save that guy. I'm sorry. Something happened, and seems I didn't save what I wrote for the previous case. Oh, I'm sorry for that. I will rewrite it again, but not right now. So what I was talking about, I said the third case is, the second case is If alpha square is less than omega O square, then I of t should be equal to beta 1 times e to the power negative alpha t times cosine omega dt plus beta 2 times e to the power negative alpha t times sine omega dt. And omega d is equal to square root of alpha square negative of omega O square negative alpha square. And case 3 is, I can copy those. And instead of writing them again, because it seems he didn't save them. So here, natural response, I'm sorry for that, of series RLC. Which is that guy. This is C, this is L, and this is R, this is I of T. Let me put that here. These are the three different cases. I'm concluding them again. In case of, we are talking about natural response RLC. So if alpha square is greater than omega square, it's overdamped, and I of t is equal to a1 times e to the power s1t plus a2 times e to the power s2t. Case 2, if alpha square less than omega square, it's underdamped, and I of t is equal to beta 1 times e to the power negative alpha t times cosine omega dt plus beta 2 times e to the power negative alpha t times sine omega dt. And case 3, if alpha is equal to omega, at that time, I can say that I of t is equal to d1 times t times e to the power negative alpha t plus d2 times e to the power negative alpha t. This is in case of what? In case of, we are talking about series RLC and natural response. Again, don't forget that alpha is equal to R over 2L and omega is equal to square root of 1 over LC. Let me repeat the last case, which is in case of step response of series RLC circuits. So I have that circuit. This is VF. And this guy is C, this guy is L, this guy is R, and this guy is VC of T. So what is needed? Again, I have to calculate alpha and omega. So the first step is to find alpha, where is alpha equals R over 2L, and omega O is equal to 1 over square root LC. Then if alpha square is greater than omega O square, then this case VC of t will be equal to VF plus A1 prime times e to the power s1t plus A2 prime times e to the power s2t. Again, from where I can find A1 and A2 prime? From the initial conditions. And don't forget that S1 or 2 are equal to negative alpha plus or minus square root of alpha square negative omega square. If alpha square is less than omega square, at that time I can say that VC of t is equal to VF plus beta 1 prime times e to the power negative alpha t multiplied by cosine omega dt plus beta 2 prime times e to the power negative alpha t times sine omega dt. Again, what's omega d? Actually, omega d is equal to square root of omega square minus alpha square. But the last case is if alpha square is equal to omega square, at that time I can say VC of t is equal to VF plus d1 times t times e to the power negative alpha t plus d2 prime times e to the power negative alpha t. Again, from where I can find the values for d1 prime and d2 prime from the initial conditions. This is what I would like to mention for today's class. If I have parallel RLC circuit, natural response, I will calculate alpha and omega, then I will choose one of three cases. If I have step response parallel RLC circuit, I will calculate alpha and omega, then I can choose one of three cases. If I have natural response RLC circuit, but series, I will calculate first alpha and omega, and then I will choose one of three cases. If I have a step response, I have to calculate alpha and omega first, and then I will choose one of three cases. This is what I would like to talk about today. Next class, I'll show you different examples which are talking about parallel and series RLC circuits, step and natural response. Again, the first step for solving such a problem is I have to choose one of those four circuits. And after defining my problem, if I have many are connected in series and parallel and L and C, so I have to simplify the circuit to be one of those four different circuits. And after that, I have to calculate alpha and omega based on my circuit. Then I will compare. Then I will choose one of three different cases. Thank you for listening to today's class, and I'll see you all next class to talk about some problems related to that topic, and after that we will talk about the last thing, which is how to solve a problem by using steady state and phasors. Thank you, and I'll see you next class. Bye for now.